રોવે કેમ રોવે મમ્મી કેમ રોવે કેવા ડાકીએ ફોટા તને કે કાણું પાડું અહીંયા કાણું પાડું પછી રિજેક્ટ કરવું કઈ
completion certificate was यहाँ काढ़े की थी नहीं बनता में जान किया गया
Good morning, everyone. So let us continue now. Yesterday we were just talking about what a meter bridge looks like. Yeah, no problem. I've not started anything yet. Okay. We talked about what a meter bridge looks like. Okay. And now we will see how it or how right, how we can use it. So basically, again, like I said, it is just this is just a practical way of using the Wheatstone bridge idea or principle, right? Okay, so instead of having to continuously change resistors from one to another, this method or this kind of instrument allows us to measure the or find out the unknown resistance in a very simple way, right? In a very simple way. Okay. Okay. Can you all see the screen now? All right. What we have here is this sliding contact, right? That's called jockey. Let's continue from there, right? Now, you see here also the purpose or the way we do it is similar to what we have talked about in Wheatstone bridge. As we slide this jockey either left or right. Okay, as we slide this jockey either left or right, what happens is the resistance of the part of the wire will change. All right. Okay, the resistance of the part of that wire is going to change. Okay, so that means if you're now going to move this wire, if you are going to slide this, let's see what happens. Okay, so let's say that this would have some length, right, till here. For example, right now in this position, let's say it would have some length, maybe 80 centimeter, right, and let's say this length is 20 centimeter. So what happens is that the resistance of this part and resistance of this part, they are proportional to the length. I hope you all remember that R is proportional to the length, right? So as you slide this wire, as you slide the jockey, as you would slide this jockey, okay, let's say you move this, you slide this towards left side, so this length on left side will decrease and the length on right side will increase, right? Again, this is what I'm saying, right? Because for that wire, resistance is proportional to length. So if you change the position of the jockey, right, if you would change the position of the jockey, then the length would change on that part, and if the length would change, then the resistance would change. All right. Okay, so here again the basic idea is same. We will keep sliding this, until the galvanometer shows zero current. Okay, we will keep sliding this until the galvanometer shows zero current, right? So that's what we are basically doing. So let's write it now. Again, this is extremely practical, like I've mentioned. Okay, so you could just, if you're writing an answer, you could just write one simple sentence as follows, that meter bridge works on Wheatstone bridge principle. Okay, I'm just helping you write a theory. Okay, meter bridge works on Wheatstone bridge principle. All right. Okay, its circuit is as shown here. બસ એટલું લખી નાખવાનું, બરાબર? Okay, then you write that J is a sliding contact. J is a sliding contact bracket jockey. On a uniform wire of length 1 meter. આ બધું description છે આ circuit નું. Okay, right? I hope you understood that. Clear? So this is the description. Now let's write what we do. So we can just say we slide the jockey until the galvanometer shows zero current or no deflection. Right? We slide the jockey until the galvanometer shows zero current or no deflection. No problem, Dhaval. I understood what you said. Okay. Right. Guys, just give me a minute. Okay. I'll just come back. Right. 1 minute only. All right. Okay. Let's continue. So I was saying that we are going to slide the jockey until the galvanometer shows zero current, right? This is again exactly, this is exactly the same as it used to be in Wheatstone bridge, right? I hope you understand that, because in Wheatstone bridge you keep changing resistor until you find the galvanometer showing zero current. Here what we are doing is we are sliding this J, we are sliding this jockey, we can move it left, right, anywhere on this wire. All right, we can move this anywhere on this wire until the galvanometer shows zero current. Okay, so I hope you have understood that. Now why to do it like this, right? And what's the use of Wheatstone bridge principle here? Let's talk about it. Okay, let's talk about it. So suppose this P is the point, or rather let's just write it as J. Okay, no problem. So if you look at this circuit carefully, if you look at this circuit very carefully, you are going to notice that this is actually a Wheatstone bridge. Have a look how. Current will flow from this battery, it will reach A, right? Then at A there are two branches. I hope you realize some current might go here and some current will start flowing here. Did you understand? Yes or no? Did you understand the two branches from A? All right. Okay. So now if from here there are two branches, so this current I2 will flow all the way through this resistor, all the way through this. Now look at C to J. Look at CJ. Do you realize that this is actually a cross connection, a bridge between two branches? Yes or no? Do you all realize that CJ is a cross connection or bridge between two branches? Okay, so I hope now we have understood that this circuit is actually a Wheatstone bridge, right? Okay, this circuit is actually a Wheatstone bridge. So let's write that now here. Okay, the circuit is a Wheatstone bridge with resistances as follows. Okay, so we can say that this whole circuit is actually a Wheatstone bridge with following kind of resistances. Have a look at this very carefully. This is epsilon, right? Okay, right? All this part is same, right? You don't have to worry about what's here. It's not important. From here you can realize that one branch goes to C, and between A and C there is the unknown resistor R. Agreed? Between A and C there is unknown resistance R. We don't care what's the resistance of the whole wire, Avinash. It's not important, right? So again, between A and C, there is unknown resistor R, right? Okay. Further, between C and B, there is a known resistor S. I hope you understood that, right? I hope you got that. Clear? Right? Everyone sees that between C and B there is known resistor S. Okay. Then, if you look at A to J, that is one part of the wire, right? So do you realize that actually A to J, suppose here is J, is one resistor which is actually equal to resistance of the wire from A to J. Did you understand this? I'm actually concerned about this one. Did you understand? This is the resistance of the wire from A to J, right? Actually, I've not been able to draw it in a shape that you would like, right? But I'm sure you will understand, you will be able to see that it's actually a Wheatstone bridge. Let's say B is here, that would make it easier, right? Okay, Now, Avinash, you will get answer to all your questions. Please don't be impatient. Now, what next? From J to B, there is another wire or another part of wire, right? Okay, which has resistance, let's say equal to RJB. Clear? This has resistance equal to RJB. Again, this part has resistance equal to RJB. That is resistance of the wire between J and B. And then I hope you realize that here between these two we have a galvanometer and like this, correct? Okay, I hope this whole part is clear, right? So this is how actually this is a Wheatstone bridge, right? This is how this whole circuit is a Wheatstone bridge. Now below it we are going to write આખી circuit તમે પૂરી કરજો જેમ અહીંયા છે એવું જ અહીંયા કરવાનું. Okay, where RAJ is equal to resistance of wire, RAJ equal to resistance of wire from A to J, and RJB equal to this. Okay, right? Clear? Okay, so now I hope you have drawn it. I hope you have written this. Now we are going to the next page. So I am going to change this, right? So when the bridge is balanced, when the Wheatstone bridge is balanced, right? When the bridge is balanced, current in galvanometer is 0, right? Okay, when the bridge is balanced, the current in galvanometer is 0. That point on wire is called null point. This is a very important word. Everybody, please remember this word, right? When the bridge is balanced and the current in the galvanometer is 0, at that point, the point on the wire, the point on the wire is called null point. Okay, again, null stands for 0. આનો શું મતલબ છે? Let me tell you that. Okay, I'm drawing this rough diagram here. You don't need to draw this. આ તમને સમજાવવા માટે draw કરું. Suppose you connected things like this. Okay, this is a rough sketch, right? Let's say it was like this. Fine. And you are sliding the jockey. Here you put it. Okay, it's not 0. તમે થોડુંક આમ slide કર્યું. Okay, it's still not 0. Finally, when this comes here, this galvanometer is showing 0 current. So this point for which the galvanometer shows 0 current, that point is called null point N. Is that clear? It's called null point N. લખી નાખો એવું N. Did you understand this? What is null point? બધા point પર 0 નો થાય હો. Right? This point is called null point. એવું એક જ point પર થાય. It will not happen at multiple points. Right? Okay, now see, why should that happen? Think about it carefully. This is A, here is unknown resistor R, this is known resistor S, this is N, and this is B. Right? So let's continue with the derivation. આ diagram draw નહીં કરો તો ચાલશે. Okay, not for exam. But now the next point we will continue, right? Okay, for balanced condition, you are going to have R upon RAN is equal to S upon RNB. Clear? હવે કેમ n લખ્યું, j કેમ ન લખ્યું? I'm asking you, why not j? Why did I not write j? Yes, this relation is only true. This relation is only true when you put or when jockey is at null point. I hope you understand this sentence, right? This relation is only true when jockey is at null point, right? It will not be true in any other case. Yes, that's right. It is balanced only over there, right? So let's continue. So now it's very simple. See, now it's very simple here. બસ બે સ્ટેપ અને unknown resistor મળી જાય. So R upon S is equal to, right? Okay, fine. Now if you write, let null point be at length or distance j લખો એ, okay, L1 from A. See, what does this mean? Go back, revisit the diagram. Let null point be at length L1 from A. એટલે અહીંથી અહીંયા null point આવ્યો L1. Clear? Okay? Right? Let null point be at length L1 from A. So I hope all of you realize that this remaining length is going to be 1 minus L1. Clear? કાં ખાલી L લખો તોય ચાલે, મેં L લખ્યું, L1 લખ્યું, ચાલશે. ચલો અહીંયા L લખો તો પણ ચાલે. Suppose this is L. Okay, L or L1 doesn't matter, right? Why is it 1 minus L? Why is it 1 minus L? આ ક્યાંથી આવ્યું? Why is it 1 minus L? Hurry up, come on. Yes, total length of wire is 1 meter. Very good, very good. So then you can write RAN upon, અહીંયા L કરું છું, L, કારણ કે આમાં એક જ લેન્થ છે, બે શું કામ લેવી જોઈએ? RAN upon RNB is equal to L upon 1 minus L, because we are writing in meter. Okay, એટલે 1 meter. Is this clear? This is the reason. All right? Yes. Okay. Right. So let's put it here. Therefore, final step, R upon S is equal to L upon 1 minus L if you are doing this in meter, and if you are writing L in centimeter, then you should write it like this. I hope you are not surprised by this. Okay, whichever you like, both relations are same. Okay. So from this, if we know S, right, we can just measure the length. L ની value છે જ, એ કેવી રીતે measure થાય ખબર છે? આની નીચે છે ને આની નીચે એક સ્કેલ મૂકેલી જ હોય actual instrument માં. આ વાયરની નીચે છે ને આવી રીતે એની પાછળ આમ એક સ્કેલ હોય, તો તમે જેમ સ્લાઇડ કરતા જાઓ ને એમ માર્કિંગ જોતા જવાના, and it's very simple, so you can easily measure the length. Is the null point exactly middle of the wire? No. તો કરવાની જરૂર જ શું? જો પહેલેથી ખબર જ હોય કે null point mid point જ છે, તો જરૂર જ નહીં ને. null point actually ગમે ત્યાં હોય, right? You will have to slide it and find it. Okay, I hope everyone realizes that null point is not necessarily at the midpoint. નહીતર તો experiment કરવાની જરૂર જ નહીં, તો આવું જ ન કરી નાખાય સીધું. Think about this. R upon 50 એટલે 0.5, half wire, is equal to S upon 0.5. So this will only happen if R is equal to S. I hope you understood that, right? Midpoint will only happen if midpoint is null point only if R is equal to S, right? એટલે generally આવું થાય નહીં. Okay, so null point could be anywhere. તો આ જો આ કેટલું ઈઝી છે, આમાં ક્યાંય એકય વાર સ્વિચ બંધ કરવાની જરૂર નહીં, કંઈ કાઢવાની જરૂર નહીં, કંઈ બદલવાની જરૂર નહીં, ખાલી ઓલી જોકી હોય એને પકડી હાથથી આમ પેનની જેમ આમ 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 કરવાનું, જ્યાં ઝીરો દેખાય અહીંયા ઉભું રહી જવાનું, ચલો કામ પૂરું, and measure length and divide and get answer, right? You understand what I'm saying? So this is so easy, right? This is so easy. ઓલામાં તો વાયર કાઢો, પછી રેઝિસ્ટર બીજું લગાડો, પછી બેટરી ચાલુ કરવાની, કેટલા બધા પ્રોબ્લેમ્સ થાય, right? So here there is no such problem, right? So this is what meter bridge is. બરાબર? Any questions about meter bridge now? Avinash, I hope your question has been answered. I hope your question has been answered now. Is it same as using variable resistor in Wheatstone bridge? Yes, Srusti, it would be same. It would give you the same value, but there's only one problem. The variable resistor that you are using, should give you known value, right? Should give you known value, right? કારણ કે જનરલી છે ને વેરિયેબલ રેઝિસ્ટરમાં એવું કંઈ દેખાડે નહીં કે આનું રેઝિસ્ટન્સ આટલું છે, right? You understood what I'm saying? There is no dial generally, right? Okay. Swarnali, well, practically you can take, listen to this, you can take any length, right? This whole idea will still work. The only change that you will have to make is this length, right? Instead of one, then you might put something else, right? If you change the length, if you don't take 1 meter, right? If you don't take it 1, then you could take something else. Okay, so principle or the idea will still remain same, right? Okay, Avinash, we again need to measure resistance. Yes, if you do it in this manner, if you follow this procedure that we have written here, if you would follow this procedure, then you actually do need to measure or do need to know one resistor. એકય નો હોય તો ખાલી તમે રેશિયો જ ફાઇન્ડ કરી શકો, as you can see, right? If you don't know anything, you can only find this ratio, that's it. Clear? હા, આના સમજ આવશે. આ બહુ ફેવરિટ છે, સૌથી ફાલતુ છે, આમાં કંઈ કરવાનું ક્યાં છે, ખાલી આટલું ડિવાઈડ જ કરવાનું એટલે આન્સર આવી જાય, બરાબર ને? એકદમ ઈઝી. અને આ ડેરિવેશન એટલે થિયરી જેવું પૂછે છે, એન્ડ ઇટ્સ ઇમ્પોર્ટન્ટ ફોર પ્રેક્ટિકલ્સ ઓલ્સો, જો તમારે પ્રેક્ટિકલ્સ થાય તો ક્યારે, રાઈટ? ઓકે, so overall this is actually an important topic, right? So I think now we should solve a question, right? Now we should solve a question, and that is example 3.9, right? Okay, Darshi, I'll answer your question, then we'll go to example 3.9. Can we also find, is that L, Darshi, or is it I? L. Can we find L if we know R and S? Well, Darshi, if you know R and S, you can predict L, right? I hope you understand. You can predict where is the null point. right? Baki આખું you should see it practically. The whole use of this method is measure L, right? Okay, by doing this experiment, measure L by doing this experiment, and once you measure L and if you know S, then you can find out R, right? So suppose someone already knows R and S both. Suppose someone already knows what is R and what is S, then you don't need to do the experiment, correct? Right? I think that makes sense to you, because this whole thing has practical importance, or practical viewpoint, right? Understood? All right then. Example 3.9. Okay. So start reading the question, everyone. All right. So let's see what this question is. Sorali, there is no need to connect unknown resistor at positive terminal, but listen to this carefully, everyone. કન્ફ્યુઝન થઈ જવાનો પૂરેપૂરો ચાન્સ છે. કાં તો સાવ સાંભળતા જ નહીં, અને સાંભળો તો બરાબર સાંભળી લેજો, અડધું નહીં સાંભળતા. ઓકે, if you want to use this formula R upon S equal to this, then you must connect R at positive terminal. I mean R on the positive side. Okay, I hope you understand what I'm saying. If you want to use this formula R upon S equal to L upon 100 minus L, then you should connect R on the positive side, because we measured L from A. Have a look here, read this. Because we measured L from A, that's why you should connect R on the positive side. Suppose you would connect it from, suppose you would measure, if you would want to connect R on the other side, okay, let's say you would like to connect R on the other side, okay, then you are going to have, then you will have to connect the unknown resistance on this side, right? Okay, એનાથી આમ કઈ ફરક નથી પડતો, to be very frank, right? Method still remains the same, but yes, when you do your final calculations, you should be aware of it, right? એટલે બીજું કઈ એમાં કઈ ફરક નથી પડતો. all you should do is this resistance upon this length and this resistance upon this length. Okay, એવી રીતે જ કરવાનું. That is how you could deal with it. If you are writing it in centimeter, you can write it like this, right? So I hope you understand what I'm saying, right? It's not really important that you do it, that you connect R on this side, પણ એનું calculation કરતી વખતે ધ્યાન રાખવું પડે. That's all, right? There's nothing else. Clear? પછી એવું ન થાય કે unknown અહીંયા લગાડ્યું હોય, બરાબર, એને R કીધું હોય, અહીંયા S લગાડ્યું હોય which is known, અને પછી આ બાજુથી measure કરતા હોય A થી, and this length is, let's say, 15 centimeter and the remaining length is 85 centimeter. તો પછી આવું ન લખતા કે R/S is equal to 15/85. I hope you realize this is wrong. Okay. Clear? So that's all you have to be careful about. બીજું કંઈ આમાં છે નહીં. ગમે તે સાઈડ લગાડો ખરેખર કંઈ ફરક પડતો નથી. Right? Okay, Swarali, I hope you have understood. Right? Okay. The example. Right. Now, in a meter bridge, figure 3.27 textbook માં figure આપ્યો છે, આપણે જાતે ફરીવાર ડ્રો કરી લેવાનો છે. Draw it again everyone, practice થશે. So roughly you could just draw it like this. ખાલી આવી રીતે આમ rectangles draw કરી નાખવાના આવા gap વાળા. Okay, and that would do. નીચે બધું છે જ, ખબર જ છે. એક વાયર રાખી દો, થઈ ગયું. ચલો આટલું ચાલશે. Right. So in a meter bridge, the null point is found at a distance of 33.7 centimeter from A. Okay. એટલે અહીંયા R connect કર્યું હતું, અહીંયા S. Right? Is that clear? Here we have connected R and S. Okay, at that time, where was the null point? So null point 1, first situation, is at what? Is at 33.7 centimeter from A. So A અહીંયા છે. Clear? Maybe somewhere here. Right? Okay. આટલો question સમજાઈ ગયો અહીં સુધી? All right then. Okay. Now it says that a resistance 12 ohm is connected in parallel with S. The null point occurs at 51.9 centimeters. So this is case 1. Now case 2. Again the same diagram. ઓકે, ચાલે, આપણે બહુ એક્ઝેક્ટ ડ્રો કરવું જરૂરી નથી. ક્લિયર? Now the new null point is maybe somewhere here. Right? So N2 is at what? Okay. Right. So now based on this, we have to find values of R and S. See, even here, everybody, even here, we need one known resistance. છે ને? કયું છે known resistance? 12 ohm. Right? We have that one known resistance. Okay. So without that one known resistance 12 ohm, it is impossible to use this whole instrument. I hope that is absolutely clear. Right? Wheatstone bridge no કંઈ પણ થાય નહીં જો if you don't know one known resistance. All right? So please keep that in mind. You could say this is a limitation of this method. Right? You could say that this is a limitation. Right? Okay. So now based on this, we are going to calculate. So first of all, for 1, okay, very simple. I'm just going to do it very fast. Clear? I don't think anyone has any problem with that. I've used the Wheatstone bridge equation. Right? I've used the Wheatstone bridge equation, balanced condition, null point. Null point means it's balanced. કીધું જ છે. Right? Here this galvanometer will show 0 current. All right? Null point. Okay. Now for second. See, one thing is clear. For second, it's not S alone. These two are together, right? So we have to take their equivalent. Okay. So શું આવશે? R upon 12S upon 12 plus S, right, is equal to 51.9 upon 48.1. Yeah, correct. Clear? Are both equations clear? Yes or no? Okay. I'm just going to drop one hint and I'll leave the rest of calculation for you, everyone. See, from the first equation, you can put R upon S value, right? What is R upon S value? It is this, correct? Just write it, just plainly write it here. બાકીનું બધું એમને એમ રહેવા દો એટલે S મળી જશે. I hope you understood that. Okay? So if you put R upon S value here, you'll get S. Once you get S, you can find R also. Mission accomplished. Okay? So that's it for this question, right? That is it for this question. Lokilo, I'm giving you a few seconds. Homework question for you. Exercise question 3.10. Okay, 3.10 is homework. All right. Okay. Tanai, these two are in parallel. 12 ohm and S are in parallel. બરાબર ને? Right? So we are using the parallel formula. Okay, so this is it, right? Let's go to the next topic now. All right. The next topic is potentiometer. The next topic is potentiometer. I'd like to tell all of you, please understand the concept. Because let me start with my own experience with this when I was in 12th. પહેલા મને સ્ટાર્ટિંગમાં એવું લાગતું હતું કે પોટેન્શિયોમીટરના ક્વેશ્ચન્સમાં તો ઇક્વેશન યાદ રાખવી જ પડે એવી છે અને કેટલું બધું છે કંઈ ખબર જ પડે એવું નથી, રાઈટ? પછી મને તો આ એચસી વર્મામાં ને એવી બધી બુક્સમાંથી તો એક ક્વેશ્ચન જ કંઈ આવડતા જ નહીં ત્યારે પોટેન્શિયોમીટરના તો. Then finally I realized that just by using a very simple idea, that in parallel voltage is equal. બરાબર ને? આ તો તમને બધાને આવડે જ છે ને? Using that you can solve nearly every question of potentiometer, however tough it might be. Right? Using this concept, using this basic concept, right, we can solve nearly every question of potentiometer. પછી તો એવું સરસ આવડી ગયું ને એમાં, right? So by the time I completed my 12th, I really started loving potentiometer questions, right? જ્યારે થર્ડ અમારે આ ચેપ્ટર ચાલ્યો તો અમારે થર્ડ જ હતો લગભગ આ ચેપ્ટર અમારી ટેક્સ્ટ બુકમાં, જૂની બુક હતી ને એમાં, right? But then I started really liking this question or these kind of things, right? Okay, so again the derivation is also very simple. ખાલી એનો ડાયાગ્રામ છે ને એ થોડો ડરાવી નાખે એવો છે. Okay, so please focus on the concept. ડાયાગ્રામ ડ્રો કરવાની પ્રેક્ટિસ પછી ઘરે કરી લેજો, 5 વાર ડ્રો કરી નાખજો. Right, let's see what it is now. First of all, I would seriously recommend that you do not worry about textbook diagram right now. Okay, we will draw it. I'll explain what is the textbook diagram later. Okay, let's draw a simplified version. Okay, let's draw a very simple version of it, right? First of all, a potentiometer has a cell, right, of let's say EMF epsilon, right? Okay, and along with it, of course, we connect some external resistance. Generally, this is a variable resistance. And R0 કહી દો તો ચાલે કે R1, RL અલગ અલગ લખતા હોય છે. RL actually stands for large resistance. Okay, RL actually stands for large resistance. Okay, so it really depends on what you want to write. Okay, fine. So that's not important. What is important is we can change this, and again its purpose is only to limit or reduce the current. Okay, બીજું કઈ નહીં, right? એટલે કઈ બળી ન જાય. Its purpose is only to limit or reduce the current. અરે RV લખો તોય ચાલે, વેરિયેબલ રેઝિસ્ટન્સ હોય. ખરેખર તો આ છે ને રિયોસ્ટેટ હોય, RH લખવું જોઈએ, RH રિયોસ્ટેટ. Okay, but anyways, all that is not useful for us, right? જે તમારે સિમ્બોલ અહીંયા બુકમાં લખ્યો હોય તમે લખો, એ લખી નાખજો, નો પ્રોબ્લેમ. ઓકે, then there is of course a key and all that, પણ એનું બહુ ટેન્શન ન લો. again this is only the simplified diagram. એક્ઝામમાં તમે આ ડ્રો ન કરતા, પણ જ્યારે આપણે સમ્સ કરવાના હોય ને ત્યારે આવો જ કરાય. એટલે આનું કંઈ બહુ ખરેખર કામ નથી. આઈ એમ ગોઈંગ ટુ ઇરેઝ ઇટ, રાઈટ? જવા દો, ઉડાડ દો, કંઈ કામ નથી. આપણે ક્યાં અત્યારે પ્રેક્ટિકલી કરીએ છીએ. and then with this battery there is a very long thick wire. Okay, slightly thick wire, and it's also quite long. Okay, આ વાયર છે એટલે આવો રોડ જેવો ન હોય, પણ તમને દેખાડું છું, બરાબર? ક્લિયર? So this wire is called potentiometer wire. Okay, this wire is called potentiometer wire. Okay, right? Now આટલું જે છે ને, આટલા આ જે રેક્ટેંગલ ડ્રો કર્યું ને, આટલો જે પાર્ટ હોય ને, that is potentiometer wire, right? And this cell that we have drawn, પછી એમાં જે કંઈ switch and etc અહીંયા આટલામાં જે હોય ને, this is called primary circuit. Okay, આટલું જે છે ને, that's called primary circuit, and this cell is called primary. Okay, primary cell or anything. જો આ primary word બે ત્રણ જગ્યાએ યુઝ થાય છે, so you have to be careful. This is called primary of the potentiometer, right? Or primary cell of potentiometer, right? Because it is in the primary circuit. એવી રીતે, બીજું કાંઈ નથી, right? Same word is used in different meanings, so be careful everyone. Now આટલું તો હોય જ, પોટેન્શિયોમીટરમાં આટલું તો હોય જ, બરાબર? Right? Then this potentiometer actually has two purposes. I repeat, potentiometer actually has two purposes, right? Okay, પેલા બે પોઈન્ટ મૂકી લેવા દો, A B, બરાબર? આવી રીતે જેવું મીટર બ્રિજમાં હતું એવું જ છે, right? Potentiometer has two purposes. Which two? એ લખી લો પહેલા, ચલો. Two purposes, right? It has two uses. Which two uses? Number one, to measure EMF of cell or battery, right? To measure, actually measure કરતા સારો વર્ડ છે ને compare છે, everyone, right? You will learn this in chemistry. Why I am saying comparing is a better word than measuring, right? તમને એમ થશે આને શું કેમિસ્ટ્રી સાથે લેવા દેવા હોઈ શકે? આવશે ઇલેક્ટ્રોકેમિસ્ટ્રી ચેપ્ટરમાં. સેકન્ડ, to measure internal resistance of a battery. right? These are the two basic purposes of a potentiometer, right? બાકી એક વસ્તુ તો ફિક્સ જ છે. Listen to this carefully. The general purpose or general use, ગમે તે કરો, potentiometer, what it is doing is, in general, it is measuring potential difference. એટલે જ એને કહેવાય potentiometer. I hope that makes sense, right? General use, or basically what potentiometer is doing is it's measuring potential difference. But if potential difference measure કરીને આપણને શું મળે? આપણને આ બે મળશે. That's what we are going to talk about, right? Clear why it is given this name? પછી આ ટોપિક પતી જાય ને પછી એક બહુ ખતરનાક વસ્તુ તમને કહેવાની છે, right? About cells, which I didn't mention because I thought I'll keep it for the end. ત્યારે વધારે મજા આવશે, તમને સમજાશે સારું. Okay, so right now we are going to talk about circuit for purpose 1. બરાબર? આ simplified circuit લઈ અને આપણે આગળ જશું હવે. બરાબર? Again, I will only worry about the simplified version right now. બધું થઈ જાય ત્યારે હું તમને ઓલો ડાયાગ્રામ સમજાવી દઈશ. બુકમાં જે છે એવો ડ્રો કરીને અથવા એમાંથી કોપી કરીને. That's the advantage of online classes. ક્યાં ગયો ડાયાગ્રામ? ખબર નહીં કોપી થાય છે કે નહીં. પૂરે right. અરે યાર. Okay, let's keep it here. Now, first one, what's the first purpose? Measure or compare EMF, right? To compare EMF. All right, so let's talk about that. Listen to this very carefully. With the point A, આમાં જે રીતે આ મેથડ છે ને એમાં કમ્પલસરી કે આ બાજુ કરવાનું. તમે ઊંધું કરો ને તો ડેરિવેશનમાં ચેન્જ કરવો પડશે. ઓકે, so please follow what I'm saying. With this point A, you take a wire out, okay, and here you connect a cell, okay, with unknown EMF. Okay, this cell has unknown EMF. All right, how much? Let's say epsilon 1. Clear? Let's say epsilon 1. એનું પોતાનું internal resistance એ હોય. Clear? I hope this is clear, right? Let's say this is unknown EMF, right? Epsilon 1, and along with its own internal resistance R1. પછી આ જે એન્ડ નીકળે ને બહાર, એટલે એક સાઈડ તો ડાયરેક્ટ એ પર લગાડી દેવાનું અને બીજી સાઈડ છે ને ગેલ્વેનોમીટર લગાડી દેવાનું. And a jockey again. Clear? Is this clear circuit? This circuit is clear? તો આ જે એક્સ્ટ્રા ડ્રો કર્યું ને ગ્રીન વાયરની ઉપર, that is called secondary circuit. Clear? Okay, all that is drawn in blue or cyan, that is secondary circuit, right? Green wire થી ઉપર જે કંઈ છે એ બધું secondary circuit. So we connect it like this. અને પછી શું કરવાનું? Let's write the method. Okay, જો આમ મેથડ બહુ જ સિમ્પલ છે, બરાબર? બહુ જ સિમ્પલ મેથડ છે આ. Okay, so if this, now that we have talked about this circuit, right? હવે એક પેલા ટર્મ સમજાવી દઉં. This is a common term, right? This term is used for both purposes, right? અને પોટેન્શિયોમીટર ને એપ્લિકેબલ છે. સો લેટ્સ રાઇટ ધેટ. Okay, for the uniform potentiometer wire, એ યુનિફોર્મ જ હોવો જોઈએ. યુનિફોર્મ ન હોય ને તો એરર આવે એક્સપેરિમેન્ટ કરવામાં. રાઈટ, ફોર યુનિફોર્મ પોટેન્શિયોમીટર વાયર આર ઇઝ પ્રપોર્શનલ ટુ એલ. આવું તો ઓલામાં આવ્યું હતું, બરાબર ને? રાઈટ, ઓકે. So you could write potential difference per unit length of wire. Potential difference per unit length of wire. Right? આવું કહેવાય કે નહીં? Right? Okay. Now V upon L. V upon L. V એટલે potential difference છે. તો suppose wire નું total resistance R હોય, right? So let's say the whole wire has total resistance R. So V is equal to IR by using Ohm's law, right? V is equal to IR by using the Ohm's law. હવે zoom out કરીશ તો કઈ દેખાશે નહીં, right? ચલો વાંધો નહીં, એવી રીતે ટ્રાય કરીએ. મને right, I hope this is good enough. Right, so what we have is, if you consider potential difference per unit length of wire, V upon L is IR upon L, right? Clear? So based on this, if you say that some current I is flowing, let's say some current I is flowing here in this potentiometer wire. So because you could say that as I is same through the whole wire, right? As I is same through the whole wire in null point condition. Okay, what is meaning of null point condition? યાદ છે ને? What is meaning of null point? આ જોકી છે, અહીંયા null point આવશે તો શું થશે? Jockey is zero, Darshi. Current in galvanometer is zero, right? So there will be current in galvanometer is zero. એટલે અહીંયા suppose 1 ampere current આવે, so that same 1 ampere will go here. I hope you realize that, because there is no current here in the galvanometer, right? Okay, so I'm saying that as I is same through the whole wire in null point condition, right, we are also going to have V proportional to L. આવું કેવી રીતે થાય? Think about it. I is same everywhere. રેઝિસ્ટન્સ તો કંઈ ચેન્જ ન થાય ને. વાયરનું રેઝિસ્ટન્સ તો એક પર્ટિક્યુલર વાયર લઈ લીધો, એનું રેઝિસ્ટન્સ તો કોન્સ્ટન્ટ જ હોય. L, that total length of the wire is also fixed, right? Okay, કે ન ખબર પડી? Total length of the wire is also fixed. Clear? So that's why, listen to this, so that's why I can say V upon L is equal to constant. બરાબર ને? Now if V upon L is constant, that means V is proportional to length. Agreed? right? You can write this constant here also, okay? Any reason? Fine, fine. Now see, whenever we have it like this, okay, v upon L is constant, so we give this constant a name, right? We are giving this constant a name, and this is called potential gradient. I hope you have read this word earlier. Gradient no matlab થાય per unit length, correct? Right? Okay. Right? So listen to this carefully. This has been given a special symbol. We write it as phi. એક લાઈનમાં લખવું હોય તો લખ નાખો, વાંધો નહીં. V by L is phi, એવું લખવું હોય તો વાંધો નહીં. ઓકે, એટલું લખી નાખો. So this phi is the potential gradient of the wire. Okay, this phi is the potential gradient of the wire. Okay. Now, based on this we are going, હવે જો આટલું સમજાઈ ગયું હોય ને તો પછી આ તો સાવ નાનું છે, અહીંયા જે સમજવાનું જ ને, right? So let's start with that. Okay, so you could write for, or we could just write, we slide the jockey until we find the null point. Okay, we slide the jockey until we find the null point, right? And let's say that let null point be at length or distance L1 from A. Okay, આમાં 1 લખવું જ પડશે, આમાં નહીં ચાલે. Let null point be at length L1 from A. So what have we indicated? That we are sliding this J left and right, and suppose we find the null point. Okay, suppose we find the null point. અહીંયા હું ફરીવાર ડ્રો કરું છું કારણ કે મને વારે ઘડી ઉપર જોવું નથી ગમતું. Okay, we only need to draw the secondary circuit. Primary નું કંઈ કામ નથી, બરાબર? અહીંયા વાયર છે, બસ એટલું ડ્રો કરીએ, right? And let's say that this is null point. Okay, now comes the most important part of this thing. Keep this diagram in mind, everyone. આ length L1 છે. Here the current is 0, right? I hope that is clear. And here there might be some current, we don't know how much that is. Let's say here that there is a current and here the current is 0, I1 is 0. Clear? Okay, diagram clear, everyone? Is the diagram clear? હમણાં જવા દઉં છું, don't worry. બ્રેક લેશું આપણે. Is this clear? Okay. So think about this carefully. આ લખતા નહીં, આ ખાલી એમને એમ સમજાવું છું. Is battery connected? કઈ બેટરી? આ જો જે ફિગરમાં ડ્રો કરી છે, this battery. Is this battery connected parallel to wire AN? Yes or no? Is this battery connected in parallel to wire AN? Yes or no? Okay. અમુક લોકોને સમજાઈ ગયું, અમુક લોકોને ન સમજાણું, કઈ વાંધો નહીં. Well, frankly speaking, it is not connected parallel, but it will still behave like that. Why? Because see, because the current is not flowing here, there is no current here, right? I hope you understand. So this galvanometer is not serving any purpose. Barabar? Okay, what I am saying is, suppose you know that current is zero. હવે જોકીને નહીં હલાવવાની, keep it here and then remove galvanometer and connect it directly by wire. કઈ ફરક નહીં પડે. Agreed? Yes or no? મન લાગે તમને અઘરા મેથ્સ થી સમજાવવું પડશે. હો, તમે ઇન્ટ્યુટિવલી નથી સમજી શકતા. Okay. So for those who have understood, let me just write one line. Okay. Right. For those who have understood, let me write one line. Okay. And for those who have not, I'll give the explanation after that. Okay. So if you have understood that these two are going to behave like they are in parallel, so directly આવું લખાય. What say? Is it clear? All right. Yes, because I1 is 0. Because I1 is 0. Right? Okay. તો જેને સમજાઈ ગયું હોય સારી વાત છે. હવે નો સમજાણું હોય તો શું કરશું? તો કિર્ચોફ લો. ઓલરાઈટ. એટલે લખવા માટે તો તમારે એવું જ લખવું પડે. હો, ઓકે, right? think of the same equation by Kirchhoff voltage law. આ ભૂલી જાઓ. હાલો આ ભૂલી જાઓ. આ નથી જોતું. આપણે આવું માનવું નથી. બરાબર ને? આવું માનવું નથી. બરાબર? નો માનો, પેરેલલમાં નથી. ક્યાં ગયું ગેલ્વેનોમીટર લો? લઈ આવો પાછો તમારા માટે. બસ ખુશ થાવ. ચલો હવે કિર્ચોફ લો તૈયાર ને? ક્યાંથી ચાલુ કરશું? ફ્રોમ A to battery to N and then to A. બરાબર? ઓકે, A G N A એવી રીતે લખવું હોય તો A G N A, રાઈટ? ઓકે, એટલે હવે આવા સ્ટેપ લખવા પડ્યો. ઓકે, સો યુ રાઇટ ઇટ. ફોર લૂપ વ્યવસ્થિત લખજો. ફોર લૂપ A G N A. બરાબર? તો માઇનસ એપ્સિલોન 1. ક્લિયર? પછી કરંટ તો છે જ નહીં, રાઈટ? સો 0 for internal resistance. This galvanometer also would have some resistance. Any instrument has its own resistance, right? This galvanometer will also have its own resistance. પણ ત્યાંય તે કરંટ તો છે જ નહીં. So that's why 0 for galvanometer. Clear? Then you come to N. Now from N you are going to A. So you are going opposite to that, opposite to the current. Clear? Okay. So ultimately, however you do it, you get this equation. However you do it, you get this equation. Clear? Okay, right, fine. Now the next step of the method. So we have got one relation. Okay, this is equation 1. Now equation 2. If we replace this cell of EMF epsilon 1 by another cell of EMF epsilon 2, right? Suppose we replace this by another cell and repeat the experiment. Okay, and repeat the experiment, we get a new null point n dash at length L2 from L2 કે L dash તમારે જે લખવું હોય. I prefer L2 frankly. I prefer it. તો અહીંયા N2 લખો અને ઓલામાં N1 લખજો. Change that. Okay, ઓલામાં N1 કરી નાખજો. બરાબર? Did you understand this whole sentence? Did you understand this whole sentence, everyone? Okay. See, there is actually one more way to write this. Look at this. Look at this. AN is a part of wire. So this is actually potential difference on wire, correct? So I hope you realize that we can also write it like this. V upon L is equal to 5. આવું હતું ને કે નહોતું? I hope it is clear to all of you. How many of you understood this? ઓકે, આવી રીતે તમને ઈઝી પડશે અને મારા ખ્યાલથી બુકમાં આવું જ કંઈક આવી રીતે કર્યું છે. કરંટથી નથી કર્યું, કંઈ ફરક ન પડે, સેમ સ્ટેપ થાય, બધું એ જ છે, ખાલી લખવાની મેથડ. So like that, if you do it here, you're going to get something like this. Right? Second case માં null point suppose N2 હોય તો RA N2, right? આવી રીતે આવશે. So if we divide equation, પતિ જ જવાય એવું છે. If we divide equations 1 and 2, આવું આવે. Clear? Okay, because phi is cancelled, right? Phi is cancelled, right? IR થી કરો તો આવું જ થશે. I hope you realize why, because R is also proportional to L. જે V proportional to L કેમાંથી આવ્યું? આમાંથી જ આવ્યું હતું ને. એટલે IR થી કરો ને તો આવું જ થાય, જેવું મીટર બ્રિજમાં થતું હતું, right? So do you realize this is very similar to the meter bridge equation? એમાં કેવું હતું? R upon S equal to L upon remaining length. પણ આમાં છે ને remaining length નથી. Here we are doing the experiment twice. Okay, one time for epsilon 1, one time for epsilon 2. Epsilon 1 upon epsilon 2 is equal to L1 upon L2. See, that's why I said we compare. Right? That's why I said we compare. So this is an important equation for us. Right? This is an important equation for us. Now, so if any one EMF is known, the other can be found, right? I think you understand that very easily, right? Yes, exactly. Okay, right? So that is it about the first purpose. Any theory પૂરી થઈ ગઈ? હજી હું તમને કહું છું ડાયાગ્રામ ટેક્સ્ટ બુક નો છે એની બહુ ચિંતા ન કરો, એ લોકોએ બહુ અઘરું બનાવી દીધું તમને અમથું અમથું, right? Okay, so this is what we have for this one. આના sums કરવાના છે, but take a break first. We will start at exactly after 6 minutes. All right, okay, break of 6 minutes everyone. See you soon. Okay, let's continue now. So we will solve the exercise question 22. Okay, exercise question 22. You can start reading it. I am copying the question, it's huge. Okay, yeah, there is still C, D, E, and F. Right. Okay. So now what we have here is that there is a potentiometer with a cell of 2 volt and internal resistance 0.4 ohm is shown. So that cell, that is of course the primary, right? This cell is the primary, right? Because you can see it is connected with the wire AB directly and there is no galvanometer, right? Galvanometer is on this side. આ સર્કિટ બેઝિકલી ઉપર નીચે ઊંધી આપી છે, જેવી આપણે ડ્રો કરીએ છીએ એના કરતા ઊંધી છે, બરાબર? Okay, so maintaining a potential drop across the resistor wire AB. So that's the potentiometer wire AB, this one. A standard cell which maintains a constant EMF of 1.02 volt for very moderate currents up to few milliampere gives gives a balance point at 67.3 centimeter length of the wire. This is from which side? From A side by default. Okay, I hope you understand. It's not mentioned in the question, but by default it is from A side. Question is not wrong. લખશે નહીં, હું તમને પહેલા જ કહી દઉં છું. Okay, all right, so this is from A side. So where is the null point? Maybe here, right, at 67.3 from this side. Okay, અહીંયા આવે null point. So when the jockey is placed here, there is no current in the galvanometer. To ensure very low currents drawn from the standard cell, standard cell એટલે right, a very high resistance of, sorry, not that one, this one. Okay, sorry, this is standard cell, I agree, right? What is its EMF? 1.02 volt. ચૈત્ય, એ જ તો થિયરીમાં હું સમજાવીને થાકી ગયો કે એવી રીતે જ લેવાનું હોય, એ ફિક્સ જ છે, બરાબર? એટલે જ તમને કહું છું કે કઈ ફરક નથી પડવાનો, ઊંધું કરો તો તમારે એ રીતે ધ્યાન રાખવું પડે. In meter bridge, in potentiometer, compulsorily you have to connect this positive towards the positive side and you have to measure the length from A. Clear? Yeah, so let's continue. So this 600 kilo ohm is put in series with it, which is shorted close to the balance point. Okay, so what that means is when we are sliding this jockey and એવું આપણને લાગે કે now the needle of galvanometer is very close to zero, right? At that time we will open this at that time we will disconnect this resistance by closing this wire, right? એટલે શું થાય, કરંટ જે કંઈ ફ્લો થવાનો હોય ને એ સીધો આમ ફ્લો થઈ જાય. Did you understand? It will bypass the resistance. Okay, all that is not important really to solve the question. એ ખાલી સમજવા માટે છે. The standard cell is then replaced by a cell of unknown EMF epsilon, and balance point found similarly turns out to be 82.3 centimeter length of wire. So I hope you realize that this question mentions two cases, right? Case 1, epsilon 1 is equal to 1.02 volt, and null point length 1 is equal to, is this clear everyone? Yes or no? થાકી જાઓ આ વાંચીને, એટલો મોટો ક્વેશ્ચન છે. ઓકે, yes it is practical question, agree. અને બધી practical ની details આમાં આપી છે, ભલે એનું કામ હોય કે ન હોય, એટલે આખું ધ્યાનથી સમજવું પડે. Case 2, unknown EMF, right? We don't know this, right? What's the balance length? 82.3 centimeter. હવે પૂછ્યું છે ને એ જોજો જોરદાર. First question, what is the value of epsilon? Okay, so what we have done is we took 1.02 volt, એનું measure કરી નાખ્યું, null point આવી ગયો. Okay, then we take another cell, we don't know its EMF, and we find its null point, and it's this. Now we have to find this epsilon. કેદે કરાય? How to do it? Come on, how to do it? How to do it? Yes, Manav. Yes, Kaya, very good. આવડી ગયું લાગે છે. હા, બધાને આવડી ગયું, બરાબર. Epsilon 1, or rather epsilon upon epsilon 1 equal to L2 upon L1, બરાબર ને? રેસિપ્રોકલ કરીને લખ્યું છે, કઈ બીજું નથી કર્યું પાછા, એમાં વિચારવા ન મળતા. હા, બસ આવી ગયો આન્સર. How many of you finished it? I'm just giving you 1 minute, all right? 1 minute only. Okay, 1.24 volt એવો આન્સર આવે છે બધા, right? Okay, next B. What purpose does the high resistance have? આટલું બધું 600 કિલો ઓહ્મ, અરે ક્વેશ્ચન માં જ લખ્યું છે. લખ્યું જ ને? નથી લખ્યું? આ લખ્યું જો, કોમ્પ્રિહેન્શન જેવું, ખાલી વાંચવાનું જ છે. Understood? Right? It will keep the current low. બસ પતી ગયું. હવે third, now here is where it gets interesting. No, wrong. Avinash, that while that is okay, but a bigger aim is that if the cell will start giving more current, right? If the cell will start giving more current, then it is possible that the cell will get damaged or that the cell will get discharged. તો પછી તમે હજી મેજર કરતા હોય ત્યાં જ બદલાઈ જાય ને, તો એ સારું ન કહેવાય, right? Okay, fine. So C, now is the balance point affected by this high resistance? is the balance point affected by this high resistance? એટલે આ 600 ohm 600 kilo ohm રાખો કે ન રાખો, will it change any of these values? What do you think? What's your answer? What do you think? All right, the correct answer is it will not have any effect, it will not change at all, right? Okay, સહેજે નહીં, nothing at all. Reason is null point on itself means the case where current flowing through that is zero, right? And if current is zero, I hope you realize that a resistor is useless, right? It does nothing. If current is zero, a resistor does nothing. I think you understand what I'm saying, right? If the current is zero, the resistor, it does nothing, right? It cannot even waste energy, correct? So it will not have any effect, right? In fact, that's the beauty of this method. Let's go back to derivation. Okay, એક વસ્તુ તમને notice કરાવડો. Here, do you see we took R1 as internal resistance of the cell, right? આમાં ક્યાંય આવ્યું? આમાં ક્યાંય આવ્યું? જો આમાં નો આવ્યું, આગળ ડેરિવેશન કર્યું, ક્યાંય નો આવ્યું. Interesting, don't you think? Right? Why does it not appear anywhere? Because this whole method is based on null point, correct or not? And what is meaning of null point? The current is zero. Now obviously if current is zero, terminal voltage V becomes equal to epsilon. I hope you remember that. And open circuit કહેવાય, યાદ આવ્યું ને? Right? Okay. Others, did you understand this? So think about it. If here, in this diagram also, if you would connect, let's say 10 kilo ohm here, it is a high resistance, આપણે લગાડી દઈએ extra, then also it will not make any difference. I hope you realize that this equation will still be the same, right? Because for null point, current will not be flowing, right? Okay. So coming back to the problem at hand. All right then. So the answer of this C question is no. બરાબર ને? Now D. Would the method work in the above situation? એટલે આ બધું સેમ છે. If the driver cell એટલે primary, right? If the driver cell of potentiometer had EMF 1 volt instead of 2 volt, એટલે શું કહે છે? હવે આ ગંદો ડાયાગ્રામ થોડો ચેન્જ કરવાનો. Instead of 2 volt, suppose this was only 1 volt EMF. Clear? Instead of 2 volt, if it was only 1 volt, would this method work? That's what they are asking. See, think about what we want to compare. Primary હવે 2 volt નહીં, 1 volt, right? Instead of 2 volt, the primary is now only 1 volt, right? But this is 1.02 volt, right? This is 1.02 volt. So અહીંયા 1 volt હોય ને અહીંયા 1.02 volt હોય, then it's definitely not possible that you get null point, right? So there will be no null point. Reason, કારણ કે આનો કરંટ આના કરતા ઓછો જ રહે, તમે ગમે તે કરો, it is impossible that they cancel each other's current. Okay. Right? Avinash, anyone else has not mentioned that, so I believe in most people's book this is the question, so we'll go with it, right? Now E, would the circuit work well? Means, will this method be a good method, a useful method for determining extremely small EMF? For example, આ 1.02 વોલ્ટ જેવું નહીં, પણ સાવ નાનું મેજર કરવું હોય તો maybe like 2 millivolt. You understand what I'm saying? Right? Okay, then would this method work properly? આનો આન્સર તમને ન આવડે તો કઈ વાંધો નહીં, બરાબર? આ એકદમ પ્રેક્ટિકલ છે, તમે આ કરશો ત્યારે તમને થોડી વધારે ખબર પડશે. The answer is no. Yes, exactly, Avinash, you understood it right. The answer is no, because if you read it carefully, if you look at this formula, then you can do small measurement, or you can use, or you can find small EMF only if you can measure small length. Agreed? Do you understand this? You can do this only if you measure small length properly. All right? Okay, but you can then maybe say we'll use a vernier caliper, right? But even then it's not going to be very helpful, right? A rather very simple way to do this is, instead of using things like vernier caliper, what we will do, instead of using a vernier caliper, what we can do is we can increase the length of wire. We can increase the length of wire and maybe take a 5 meter long wire or 10 meter long wire. Okay, we can take a very long wire, right? By doing that, what happens is, think of this carefully. Suppose, first of all, like, let's use this example. Okay, it's numbers. Like here, for 1.02 volt, we are getting a length of 67.3 centimeter, right? Okay. Yes, Avinash, that's right. So for 1.02 volt, we are getting a length of 67.3 centimeter, right? Okay, and let's say that this wire was 1 meter long. I પૂછે કેટલો છે? Otherwise, we'll just assume. Okay, not given. Let's assume that this is 1 meter long wire. Okay, let's assume that this is 1 meter long right now. So instead of 1 meter, now suppose you take 10 meter. Then that same 1.02 volt will now come at 6.73 this will come at 6.73 meter. Why? Because wire length has become 10 times. Do you understand what I'm saying? If wire length will become 10 times, then this null point length will also become 10 times for the same voltage. The reason is this: phi is V by L, and this is a constant. Did you get it? So if you increase the length, if you would take a longer wire, right, what would happen is phi will decrease. Everyone, listen to this carefully. Phi is V by L, that is constant for a particular wire and particular primary cell. right? For a particular wire and particular primary set. So if you would just increase this length, let's say you make this 10 times now, so this would decrease, and that's why for the same voltage now you need 10 times the length. Okay, so what happens is then you don't need to measure very small lengths, right? And even by using a simple ruler or a scale, right, you can do it easily. Okay, so I hope you understood the answer to E, right? The answer is that you should increase the length of wire. Take a very long wire. Got it? Okay. Now there have been some questions from your side. Let me take those questions one by one and answer those. So one question is, what is thermocouple? That was asked by Avinash. જો બહુ સમજાય નહીં તો બહુ ટેન્શન ન લેતા, રાઈટ? આ તમારા સિલેબસમાં નથી. Thermocouple is not in 12th standard syllabus anymore. What is a thermocouple? Thermocouple is a device that produces a small potential difference. Okay, battery જેવું પણ બહુ જ નાનો potential difference હોય, millivolt. Okay, it's about millivolts, right? Okay, so how is it made એ કહી દઉં થોડુંક. Thermocouple is actually a junction. Junction એટલે joint. Okay, thermocouple is actually a joint of two metals, right? Okay, and basically it's something like this. Like let's say that red is iron. For example, let's say that red is iron, right? And Cu is the copper part, right? So what happens is when you join them, because they have different tendencies, right? Because I'm sure you all realize that chemically or their chemistry is slightly different, although both are metals, right? So if you take one such joint and you take another such joint like this, okay, એટલે અહીંયા બે joint છે ને, એક અહીંયા ને એક અહીંયા, and you keep these joints at different temperatures. You keep these joints at different temperatures, right? So what happens is, because of these two different temperatures and these two different metals, there is going to be a potential difference. There is going to be a voltage developed between these two junctions. એટલે આવી ટાઈપનું જે છે ને, that's called a thermocouple, right? It is absolutely not related to your syllabus. All right, તો કંઈ ન સમજાણું હોય તો એ કંઈ વાંધો નહીં, right? Okay. Right, now there is one more question. Okay, that's from Himani. Is it necessary that current should always flow in loop? Yes, Avinash, that's right. Okay, Himani, I got your question. Then where did I go of secondary battery? There is no alternative path as in meter bridge. Okay, fine. I think we need to analyze this a little bit better so that anyone who might have had this question will understand this easily. See, so the question that Himani is asking is that if you straight drawn up to the bottom. So suppose this is that potentiometer wire, and here you have connected the primary. All right, okay, fine. And then over here let's say this is secondary, right, with its internal resistance and all that, and suppose this point is actually null point. Suppose this point is actually the null point, right? Okay, and here the galvanometer will be showing zero current, right? Here there is no current. So Himani is asking a question, where did the current of this cell go, right? Okay, right. That is close to the correct answer, Avinash. It is that why is no current flowing here, right? That's the question. The reason is actually very simple. Okay, it is that whatever EMF this battery has, right? So that's like epsilon 1. Now between these 2 points, right, between these 2 points, that is A and N, the potential difference between the 2 points A and N is exactly the same as epsilon 1, right? Okay, so what happens is as follows. Listen to this carefully. This battery is actually trying to drive, this battery, secondary cell, is trying to drive its own current, let's call it X, suppose. Okay, this battery is trying to drive its own current X through this wire, right? But when it reaches here, right, what happens is, because the potential difference between A and N is already equal to epsilon, because the potential difference between A and N is already equal to epsilon, so the points A and N behave as if they are a separate battery and they are driving a current in this loop. Okay, right? Because the loop is same and the EMF is same, so this part will try to give a current X like this. Okay, I hope you understand that. So actually the current splits in this manner. અહીંથી જે કરંટ આવે એ આમ જવો જોઈએ X, right? અહીંથી જે કરંટ આવશે એ આમ જવો જોઈએ X, but this battery here is also driving an opposite current X. So in this wire, these two currents X will be cancelled. Did you understand that, everyone? I hope that is clear. આને સમજવું હોય તો આવી રીતે તમે ડ્રો કરો. Suppose this is one battery 10 volt, okay, and internal resistance some 1 ohm. એની સાથે અહીંયા એક બેટરી લગાડી દો, right, which has some internal resistance, we don't know, okay, some internal resistance, no problem, and this is also 10 volt. તો શું થશે? Think about this circuit. Think about this potential difference between A and N. If it is 10 volt, think about this circuit. Will there be current? Will there be current here? Will there be current here? Think about it. Right? So where did the current go? It's actually cancelled. I hope you get that. Right? The current of, you could say that because both the batteries are opposing each other, their EMFs are cancelled, right? So that's what is happening here, right? The only thing is, here there are not two batteries, but this battery is indirectly giving potential difference to these 2 points, right? That's why current doesn't flow. એને block કરે છે, basically એને block કરી નાખે, right? Okay, now the second purpose the second purpose of the cell, okay, that is to measure internal resistance. All right, the second purpose of the cell is to of the potentiometer is to measure internal resistance of cell. Clear? So let's talk about how to do that. Pela any simplified circuit. Again, I would wish all of you would not worry about the actual circuit like it is given in the textbook. Okay, simplified circuit is enough. તો આમાં તે છે ને બે વાર કરવાનું. Potentiometer wire, primary cell, etc. Okay, point A, point B. Clear? આટલું તો એમાં આવશે, right? Let's say this has epsilon EMF. Then here in the secondary you connect a battery or cell with EMF epsilon 1 and internal resistance R. એટલે એક કામ કરો ને, આને છે ને આપણે આમાં એપ્સિલોન ડેશ કહી દઈ અને આને ખાલી એપ્સિલોન. ઓકે, સો એપ્સિલોન એન્ડ આર. ક્લિયર? ઓલરાઈટ? ઓકે, and we try to find the null point as usual. And we try to find the null point, right? Okay, so we write it as follows. Okay, લખાવી તો દઉં છું, બરાબર? એવું બધું નહીં લખાવવું પડે ને કે we connect a battery or a cell as shown, એવું બધું તો આવડશે ને હવે. Okay, I hope you understood what I've written here. We find null point for this cell n, right? Athwa null point n for this cell. એવી રીતે લખવું હોય તો. So let's say here is some null point n for the cell. Okay, and it is at a distance n. It is at a distance n. So this is done, right? This is done. So here you could say, sorry. Clear? આ ક્યાંથી આવ્યું? આ ક્યાંથી આવ્યું? આ ક્યાંથી આવ્યું? Everyone still there? How do you get this? Yes, by potential gradient, right? Or Kirchhoff's voltage law, જેમ સમજો એમ, right? See again, if this is a null point here, you will get zero current, right? Okay, right, fine. ખાલી next એક step કહી દઉં, પછી તમે વિચારી લેજો, right? Then we'll talk about it later. Now we connect a known resistance are parallel to this cell, એટલે ખાલી સર્કિટ ડ્રો કરીએ, પછી તમે વિચારજો કે શું થાય આવું કરો તો, બરાબર? ઓકે, so with this in parallel we connect a known resistor. Okay, clear? And then from there on the procedure is same. We connect a galvanometer and a jockey and all that, right? Okay, so you think about what happens in such a situation, right? આટલું ડ્રો કરી લો, મૂકી દો. We will continue with it the next time. Okay, I hope you are not dead by 2 hours of physics. Goodbye, everyone.